This track is sponsored by Walker and Associates. Walker and Associates is the premier source of network product solutions, providing supply chain management, network deployment kits, quality installation, systems integration, and unsurpassed service.
Hi, and welcome to the SCTE ISPE Cable Tech Expo. I'm excited to be kicking off the Fall Technical Forum today. I'm Greg White. I'll be the moderator for this session. I'm a technologist at Cable Labs and have been directly involved in helping the industry move Docsis technology forward through most of the versions over the years. For the past 3 years, I've been leading the low latency Docsis project from its beginnings as an internal innovation project at Cable Labs through the LLD working group and the interoperability events that we've been holding at Cable Labs. Prior to that, I brought both the active queue management and buffer control technologies to Docsis. So this is a subject that's near and dear to me, latency performance for broadband networks. And I'm delighted to see the level of interest now in low latency technologies across both the operator and vendor communities. So we have a supersized panel today, kicking off the Fall Technical Forums. We have 4 speakers scheduled to run for 75 minutes. So a lot of great content for you across a range of different topics relating to low latency. Starting off, the speaker will be Colin Dearborn. He's a senior network architect at Shaw Communications. His recent focus is on helping Shaw plan its network deployment of low latency technologies across their entire network of 2 million broadband subs. He'll start us off with a look at the importance of latency, where latency degradation occurs across a cable broadband network, and the steps that an operator can take today and in the near future to reduce those sources of latency. Next up will be Karthik Sanderson, a distinguished technologist at Cable Labs, who's focused on the development of new cable access network technologies. He is the technical lead and a longtime contributor to various Docsis technologies, most recently on Docsis 4.0, PMA, which is the profile management technology, and low latency Docsis. He'll be talking about measuring latency performance in broadband networks, providing a level set on characterizing latency performance, the various metrics that can be used to report on that performance, and some considerations for what goes into a well thought out latency measurement architecture. Our third speaker is Shebnam Ozer. She's a senior principal architect in the Next Generation Access Networks group at Comcast. Her focus is currently on deploying, measuring, and optimizing low latency technologies across Comcast's network. She'll be giving us an update on that work, focusing both on the near-term components as well as providing a longer-term vision for latency performance across the broadband network. And batting last, Tushar Mathur is a staff systems engineer in the CTO office for broadband networks at CommScope. His recent focus has been on ensuring that CommScope has a top-notch implementation of low latency Docsis, including representing the CommScope CMTS team at industry interoperability events and performing benchmarking of latency performance in a range of user scenarios. He'll be giving a brief overview of low latency Docsis technology and then providing us an in-depth look at the performance gains that can be achieved by using the various tools in the LLD toolbox. So without further ado, I'll hand it off to Colin to get us started.
Thanks, Greg. Good morning. My name is Colin Dearborn. I work for Shaw Cable. Today I'm going to be talking about improving the latency of an MSO network. So to start off with, why do we care about the latency of a network? Video game marketing generated over $120 billion of revenue in 2019. This is about 3 times what the movie industry generated worldwide at $42 billion. Gamers are making up a majority of the population these days. 2018 poll showed that over 64% of Canadians played a video game of some sort in the preceding 4 weeks. ISPs are starting to market to these gamers, advertising their latency results. A competitor of ours recently launched a page touting their fiber to the home network, and most of their talk is about latency and consistency. As well, some game sites even have tools to show you how the ISPs in your area are stacking up. League of Legends has an ISP leaderboard. They show a score for each ISP and even how many players are playing on each ISP. So how does cable stack up today? While fiber to home technologies are marketed with a lower latency, looking at the League of Legends report, lag report in Vancouver, you can see that a small fiber-only ISP shows a latency of around 30 milliseconds, while Shaw Cable MSO has a latency of 16 milliseconds. This shows that fiber to the home is not necessarily always better by itself. A well-connected ISP with multiple transit and peering agreements can have a much better advantage over an ISP with much less transit and peering. As well, optimizing that network ensures that you have the best connectivity available for that for your network and your latency sensitive applications. What are some sources of latency? So there are 4 major areas where we can bucket our latency. In the home, on the Docsis plant, in the core network, and on the general internet. Congestion is something that's common to all links. Congestion will increase latency no matter where it happens. Some places can cause more latency than others. In the home, we have Wi-Fi that is a major source of latency. And then multiple users on those Wi-Fi links will definitely increase latency as well. In the Docsis plant, our major source of latency is the request grant cycle. And then if we have too many users and congestion, that will increase latency. When we talk about too many users on the Docsis plant, though, we're talking orders of magnitude greater than what we'd see in the home. We're talking multiple hundreds to thousands of customers to cause any sort of problem. In the core network, again, congestion is an issue, but our biggest source of latency would be the routing to our peers in transit. If we route across the country and then back again, that's going to cause us a lot more latency than if we go with the more direct routes. On the internet, there's not a lot we can do there, mostly congestion, and the only thing we can really control is our choice of which exit point in our network to hand off our network traffic. So reducing latency. In the home, how can we reduce latency? Well, if we do wired, that will give us the best option for latency. You will be in the order of millisecond or less if you're wired in your entire network. But Wi-Fi is super easy to set up and it's portable, so customers are increasingly using Wi-Fi for a lot, if not all of their connectivity. So what can we do for Wi-Fi to make it better? Wi-Fi's latency is usually in the order of some milliseconds to hundreds of milliseconds, depending on how many devices you have at home. You can use Wi-Fi multimedia that will keep congestion down for specific applications that support Wi-Fi multimedia. It prioritizes those apps on the Wi-Fi network, and then therefore getting them on the line and off the line faster. As well, for all devices, whether they're wired or not, you can enable AQM on your routers and modems. Make sure that latency is held down, even if you have congestion on your home network or on your Wi-Fi. That'll make sure that your latency is as low as possible. On the Docsis plant, what can we do today? We've done some experiments. We've reduced Docsis map intervals to 1 millisecond or less, depending on the platform. This doesn't give us groundbreaking latency reduction, but it does reduce it by a few microseconds. If we enable AQM on the CM and CCAP, that will make sure that latency during congestion is held down. One thing we've noticed is that AQM is not always enabled or enabled with best parameters. So it's good to test to make sure that your AQM is operating as you expect. We've had some vendors have AQM settings that still enable or still allow for hundreds of milliseconds of latency. So we adjusted those to be much more acceptable. Something that surprised us a little bit was enabling OFDM in the downstream to reduce latency by up to half a millisecond. And it was regardless of how large the channel was. We tested from 24 megahertz to 192 megahertz, and the latency was reduced by half a millisecond in all cases. So that's an easy, quick win there. In the core, we did some major work in our core networks. we noticed that a complex network route hops may not adequately describe the latency of a path. So by default, your IGP will use the number of hops to determine which path is the quickest and which path to take. We found that sometimes our longer links are not as the crow flies. They go around loops into different cities and therefore get a longer latency. So what we did is we did a ping of each hop and adjusted our IGP metric to match that ping, allowing us to take a much shorter hop, even if they're a shorter route, even if there are multiple routers along the path. In the core, we disabled equal cost multipath for BGP routes that came in with the same cost into multiple. What we noticed was if this was happening, we would have routes that would go one path one day or one session, and then another path another session. It's like customers saying that their routes were good one day, their latency was good one day, and then the next day it was terrible. So what we did is we used our IGP metrics that we did earlier in the previous slide to be the tiebreaker for BGP costs. Now, this doesn't always mean that we get the best latency end to end. We choose the shortest route out of our network, and whatever path that is, go back. So, for example, if you're a customer in Calgary, and we have an equal cost in Chicago and Vancouver, or in Toronto and Vancouver to get to a router in Chicago, we'll choose Vancouver because Calgary to Vancouver is less latency than Calgary to Toronto. And then, so we'll have a little bit of a double back coming back to Chicago, a few milliseconds latency. What it did do was stop that variability of latency and allowed gamers to see that they were getting one type of latency regardless of day. In coming up in the future, so in the home we have Wi-Fi 6 OFDMA. What this will do is allow multiple devices to talk at the same time on the wire. Today, with Wi-Fi, only one device can be talking at a time, so they have to wait until the air is clear before they can start transmitting, which leads to latency and jitter on a busy network. Having OFDMA will allow devices to be on the wire pretty much instantaneously, reducing that latency and jitter. However, in order for this to work, all devices on your network have to be Wi-Fi 6 enabled. If even one device is legacy, it'll drop back to the current native talk. Another solution coming up is Cable Labs dual channel Wi-Fi. What this does, it'll add a new channel just for downstream. And then the previous channel will be used for upstream and legacy traffic. Therefore, you don't have to have all your devices being able to do this solution. And as you add more devices, it'll take more into the downstream channel, freeing up that single channel for upstream, allowing clients to get on and off the wire quicker again. In Docsis, we have low latency Docsis coming up. Tushar will go into more of the details of some of the tests that show how it improves our latency. Some of the things we're excited about are ULQ, proactive grant service, and upstream scheduling improvements. Again, other speakers will be talking more about these as we go through. We're especially excited about PGS and ULQ. For the future of the core, tuning the metrics for each hop was very time consuming in our network. So going forward, as networks become more complex and we get SIM networks in our network, we'll have way more links and things will be much more complex. So automation of these metrics is going to be extremely important. Also coming up is edge computing. As cloud gaming platforms come up and AR and VR platforms are coming up, they're looking at deploying their computing closer and closer to the customer, which will reduce the latency for those applications, removing the variability of the general internet from these applications. So in conclusion, the future looks bright. There are a lot of technologies ensuring latency is going to be low, even with congestion, even with doing a quick download, the burstiness of the network. Low latency Docsis will allow us to compete against target homes marketing of lower latency and more consistent latency. And ensuring that your core network is optimized will result in a network that will compete regardless of last mile technology. That and Karthik is the next speaker. Who's up?
Great, thank you for that, Colin. I think we'll be getting the slides queued up for Karthik to walk us through some latency measurement aspects.
All right. Thank you, everyone. Thanks for the opportunity to be here and talk about latency and measurement. I want to give credit to Greg White and Steve Glennon, my colleagues at Cable Labs. I call them the latency czars for the cable industry. A lot of this work is kind of from our internal discussion, and the thoughts are collective here. So let's get started. The management guru Peter Drucker says, if you cannot measure it, you cannot improve it. And I think that thought is very relevant to us here with latency and how latency fits in with the 10G vision. We are trying to measure the metrics so that we can share that with the public. We can share that with the regulatory bodies and things of that sort, right? So knowing how to measure and what to measure is definitely the key to get started with understanding and improving latency. So as an outline, I want to talk a little bit about the operator goals on latency measurement. I want to get to the details of the metrics, right? What metrics do we want to capture? What metrics do we, and what are the right definitions for those, and how do we capture those? I want to take us a little bit on a visual story, right? I think latency numbers kind of get a little boring, but once you start looking at them and visualizing them, you get to understand the details of how the latency behaves and varies across the network. So we'll talk about, getting towards percentile values from averages and talking about PDFs and CDFs, and we'll get to how to visualize the latency. And I want to kind of end with measurement architectures and how to actually measure latency and how an operator can set up infrastructures to measure latency. All right, so this is similar to the picture which Colin put up, and thanks, Colin. That is a great introduction to the topic of latency. We can split up the network into the home network, into the access network, and the core network. And as Colin showed, the core network could be, part of it could be the MSO network, and then external to that as you connect to various servers on the internet, right? So as a goal, an operator definitely wants to be able to diagnose issues and say, hey, Mr. Customer, this is a home issue, it's with your Wi-Fi AP, or to understand if this is a Docsis network issue, it's a Docsis upstream or Docsis downstream, and then is it something with my peering point all the way to the left, right, in the core network. So I think operators have different sets of goals on why to do the latency measurement and to use that measurement to improve the network, right? I mean, something as simple as distributed CMTS architectures and virtual CMTS. Hey, how does it affect the latency as I move the virtual CMTS to a different place? In the context of latency measurement, of course, there's the regulatory bodies like the FCC who have efforts like Measuring Broadband America and CRTC in Canada, which publish speed reports, and along with that come latency reports, right? So it definitely is getting a lot of scrutiny at a very public level. So let's start with some basics, right? What is latency, right? It's essentially the time it takes for me to send one packet from one machine to another, right? That depends on the topology and how congested the network is and things of that sort. So that's the very essence of a single measurement. Now, if I build up from that and go to a round trip measurement, the idea is I send one packet from point A to point B reflects it back to me, and I measure the time, right? So round trip. Here for this, you definitely need a process at the other end, which does that reflection for you. And it's easier to maybe implement because I don't need to synchronize clocks across point A and point B. Now to make things more interesting, instead of just sending the one packet, now I start sending multiple packets, right? So now I start getting more of a sample of how the latency behaves over time, over different times of the day, right? And how it feels and behaves for a customer, right? I can start getting an idea of those types of latency measurements. So I wanted to get to a definition of jitter or delay variation. I think this term is used a lot in terms in the industry around latency. And I think the IETF and I think Cable Labs is kind of converging around these two common definitions of delay variation, right? IPDV and PDV. So inter-packet delay variation is really is simply the measure of is the difference in latency between one packet as compared to the previous packet, right? So between two packets, what is the difference in packet arrival times, and how does that vary over time? Packet delay variation, on the other hand, says I'm going to choose a single point of reference, say the minimum latency of all the measurements that I did, and then compare those measurements, compare each packet to those measurements, right? And so that I get a variation in latency as compared to one reference point. I could choose the minimum as a reference, or I could choose the average as a reference. So, okay, so hopefully that sets the baseline in terms of what latency measurements are, one-way round trip, and also a definition of jitter. All right, so now let's get started with visualizing some of this data, right? I think so like sending one packet is and looking at a number is one thing, but looking at a test, in this case, run over 2 minutes of time, gets you to a better understanding of what's really happening. So this is some tests we ran at Cable Labs. At a very high level, I think I can say that the orange traffic at the bottom is marked traffic, and the blue traffic, the blue data series is unmarked traffic. We can easily see that they're, the orange traffic is getting the latency behavior, the low latency technologies that we have configured for that in the lab, whereas the blue ones are not, right? And you can already see that the blue time series graph is varying over time. In this chunk here, there's a speed test going on in the background, so you can see the TCP sawtooth. And you can see that latency is truly varying over time, and the experience of a customer will depend on where in this time series his experience, right? There are multiple definitions you could use, all the way from standard deviation, which will put you down at this 23 millisecond mark down here, versus a percentile metric, which is more about how much of my traffic is getting latencies below that number. So a P99 number would be around the 120 millisecond mark. If you choose maximum, then you're up at the 260 mark. A minimum is 11. So I guess the takeaway here is there can be a lot of definitions around what latency numbers on how to describe a test of latency measurement. And as they vary, you kind of want to know which definition a particular test is using, right? The same goes for jitter. There are different industry bodies which are using either the IPDV metric or the PDV metric, and they kind of vary across depending on the definition. So what's a better way to look at this, right? So I can start building a probability density function, a PDF, right? I simply histogram all the data and split it up into bins. And now a better behavior emerges, right? I can clearly tell, okay, the orange traffic, the low latency traffic is very tight and has low millisecond latency, whereas the blue, it kind of extends all the way up to, it's to the right and extends all the way as a long tail. Now, and then the shape of this histogram kind of gives you that PDF curves. How can I make it even more interesting, right? I can start doing a CDF graph of this, right? A cumulative distribution function, which kind of tells us for a given point, let's say if I choose the 50 millisecond point here, if I go up to the graph, then it'll tell me, okay, 75% of my traffic is below that. Or if I compare the two P99s for each of these graphs, then I can tell, okay, the P99 for the orange traffic is at 45 seconds, whereas for the other traffic is at 120 seconds. So this starts giving me better tools to actually analyze and look at this data. To take it one more step further, I can start looking at complementary CDFs. This is essentially the complement of the previous graph. I just invert the probabilities. And the reason I do this is really for the next step where I can look at a logarithmic CCDF where I'm trying to try to focus in on the areas which I think is very relevant, right? So the higher percentiles of latency data, like the P90s and the P99s and 99.9, I can start seeing the differences in each of those in this type of graph. So hopefully these are some tool sets which an operator can use to visualize the data. So what's with this percentiles, right? Again, a percentile is a number below which most, so if I pick the 50th percentile, then 50% of the packets get a worse latency than this. That number, right? If I, which essentially means every other packet has a latency which is higher than that. If I go up to the 95th percentile, that means 5 packets out of 100 get worse latency, right? So for a gaming application, which today is typically 60 packets per second in both directions, that means that's a latency impact 3 packets a second, right? Which is if those set of packets are sending you the game state update of you ducking behind a wall and not getting blown up, that could over time significantly affect a gamer's experience, right? So some of these higher percentile values really are trying to get us towards that understanding how this impacts and how often this impacts an application like a Zoom call or a gaming application. All right, I'll kind of jump towards measurement technologies. There are 2 measurement techniques, right, or methods. The first philosophy is active measurements. So here I am injecting traffic from point A to point D and getting the traffic back, and I'm calculating latencies based on those. So this is active in the sense that as an operator, I'm injecting traffic into the network. This is definitely very useful because you have control on when you want to run this test and when use it for diagnostic purposes and things of that sort. And you can run it under load or when you're not loaded. On the other hand, passive measurements go with the philosophy that I don't want to inject any traffic into the network to measure latency, but I'm just going to use my knowledge of existing protocols. Maybe it's a handshake with a video server, or the very simplest is just a TCP handshake. And I'm going to measure the differences between 2 of those known packets, in this case, the SYN and the SYNAC, and use that as an estimate for the latency in the network. So this is another approach to measuring latency. As an operator, when you are building your latency measurement infrastructure, I think there are a lot of considerations which you need to think through, right? Am I measuring this at 2 a.m. at night, quiet times, or am I measuring this at 6 p.m. in the evening, right? What is my measurement window, right? Am I doing this once an hour, or am I doing it once a minute, or am I doing it 50 times a minute, right? I mean, or 50 times a second even, right? Depending on how granular do I want to understand the latency effects within the network, right? And the latency numbers within the network. There's a whole slew of topics around, how do I store all this data? How do I aggregate the data? How do I get the numbers out of the PDFs and CDFs we just talked about? And how can I actually compare latency deviations over time, right? Maybe you choose the P99, maybe you choose a few more values, P90 and P50, and you compare how each of those values shift over time. If you're using infrastructure from Sam knows or other, kind of distributed measurement architectures, then there's always the question of, hey, is your measurement server within the operator network or is it off the operator network, right? And what are my latency test definitions, right? What packet sizes am I sending? Are they 100 byte packets or are they 1500 byte packets? Things of that sort. So, and then I think Colin talked about LLD, and Tushar will talk about it a little bit more. We'll talk about how to differentiate between marked traffic and unmarked traffic. So, and then how do we change the latency tests to accommodate for that? So I'll pause there. Hopefully that is a good overview of what latency is, how to visualize it, and how to measure it. I think the call to action definitely is for operators to have their own measurement infrastructure, make sure as a cable industry we can pick the right metrics and pick the right measurement architectures and tests, so that when we are sharing this latency data with the general public or the regulatory bodies, that we have our own measurements and the tests are defined by us, as opposed to having it defined by someone else and given to us. So that's what I had around latency measurement. Hopefully that was helpful. I'll turn it back to you, Greg, to hand it over to the next speaker.
All right, thank you very much, Karthik. Next up will be Shebnam Ozer. And before, Shebnam, you start, I just want to let the audience know that we will have time at the end for Q&A. And you should be able to type in questions for Q&A for the presenters via the portal. Unfortunately, I have not seen your view of it, so I'm not sure exactly how that looks, but hopefully you can get your questions entered that way, get them queued up, and then after our fourth speaker, we'll start answering those. So thank you very much. And on to you, Shebnam.
Thank you, Greg. So I will talk about the latency management approaches. And before I start, I would like to give credit to my co-authors, Karl Klasky, Dan Rice, and John Krostowski, and the LLD team within Comcast. Okay. So if we look to low latency management, in fact, it's part of the end-to-end performance management for service and customer-centric systems. So to support different customer experience for low latency services, we need to understand different quality of service metrics that both Colin and Karthik talk about. For example, Colin gave an insight on the impact of latency on gamers' experience. And then Karthik mentioned different measurement systems for these quality of service metrics. And if we have these metrics and measurements, then the next question is how we can use them to manage the system in a way that we can provide the best customer experience. In a very simple form, After we define the service and business requirements, we design the architecture for the network using programmable and abstracted resources. And then we want to deploy them, test them, deploy them in an automated way continually. And then the service assurance should be also automated based on a data-driven and knowledge-defined network. I want to emphasize 3 keywords here. The first keyword is automation. We want automation in terms of service assurance so that we can have a proactive management system using prediction systems. And we want to understand when there are issues beforehand so that we can program resources in a way that automated provisioning and configurations can be supported. The next keyword I want to emphasize is self. So we want a self-healing, self-optimizing, and self-managing system so that MSOs can support the management of automation instead of managing different network segments manually. And the last word that I want to emphasize is the recursive closed control loop model to show that this is a dynamic system that continually adapted based on the network findings. Sorry. So before I talk into the more management system, I want to mention about some latency measurements that we deploy in the production spaces. So Karthik already gave a good descriptions on these latency measurements. And the first question we have to ask is why we need these measurements. It can be because we want to understand the impact of different network configurations on the latency. We want maybe to understand the latency to a game server from a customer home, or we may want to understand the impact of network utilizations on the latency. So why is the first question we should ask so that we can define which measurements we need to do, when we need to do them, and how we measure them, where we store them, and how we use them in a data analytics system. Through the data analytics, we can also find new meanings to the measurements. We can even enhance the answer for why we need these measurements. So as Karthik mentioned, there are passive and active measurements, and I will provide some measurement examples for passive and active underload measurements. And active without load measurements are in general ping measurements that we are all more familiar with and that MSOs have been using for different connectivity and other quality of service metrics collections. So for the passive measurements example, I want to give an example where the measurement is between the client home and a server that can be in the cloud over a public internet, or it can be in an edge server. And in this example, we measure the latency by observing network traffic in a virtualized network function that is located in the headend. The traffic that is observed is the TCP handshake, and the network function only measures the latency for the TCP handshake without requiring any deep packet inspection. So that's a very high level measurements, but it provides a very good insight on the session connections, but also it can segment the latency in the access network, which we call the client round trip time, and also on the northbound of the MSO's core network, which we call server round trip time. So by observing SYN and SYN-ACK of TCP connections, we can measure the server RTT. And by observing and measuring the time for SYN-ACK and ACK, we can measure the client round trip time. So as Colin mentioned in his talk, most of the idle Docsis latencies are between 10 to 20 milliseconds. So if there is no high utilization levels, we expect to have in the order of tens of milliseconds of round trip time within the access network. But as you know, during the pandemic time, there was a huge utilization increase, especially in the upstream, it was up to 30%. And also the peak times change considerably. For example, for upstream from 9 p.m. Peak time in the upload, now we see that it is between the working hours, the whole day. And after the working hours, we have another peak, which is the entertainment peak. So with these new utilizations, and new peak times, we can see that, we have to measure latency, jitter, packet loss, and other metrics in an automated way to help us to predict the latency and to proactively find the issues, detect the issues, but also to make sure that we can fix the network before the customer experience is degraded. So these measurements that we see here is taken during the pandemic time, and still we can see that 85% of all the measurements were less than 50 milliseconds, even with very high utilization levels. And if we look to active measurements, passive measurements are like the TCP handshake measurements are good because these are the typical latencies that the customer may see under real network conditions and utilization levels. But we also need to understand the delay bounds, the latency, jitter, and packet loss bounds. So we need other types of measurements like Karthik mentioned, and I want to provide some examples for the active underload measurement. In this case, the measurements is between the RDKB router in the home and a server located in the MSO's head end. And the connection remote time, round trip time is very similar to idle time, where the latency for Docsis networks should be around 10 or 15 milliseconds. And then the next step is to measure the latency under TCP load. So TCP load here will be similar to file uploads, downloads, or streaming, where aggressive traffic can utilize most of the speed tier rate. And then in the same time, UDP requests and replies are sent, and this UDP traffic will be similar to low latency traffic like gaming, control traffic, or voice over IP type of traffic. So by measuring latency under load, we can estimate the maximum latency that low latency services may see under heavy TCP-based traffic. Why we measure this? Because at home, if we assume that a gamer is playing a game that requires low latency and low packet loss, but in the same time, other family members have file uploads or downloads or heavy streaming, then if we don't configure the system properly, we may see that this TCP traffic may have a negative impact. So in this examples, there is a network with very large downstream queues in the CMTS. So here you can see the vertical axis is downstream latency underload, and the horizontal axis is upstream latency underload. So the left graphs are before any optimization, and the right graphs are after the downstream AQM optimization that Colin mentioned in his also in his talk. So the maximum latency underload are displayed in the top graphs. And you can see that before optimization, because CMTSs may have large queues, we see a 2 seconds of latency for different speed tiers. But once we optimize the latency, we can see that the latency is improved considerably without decreasing the quality for other services or impacting the speed tier or packet loss. So the important part is to understand how we measure the latency and how we can use them to detect areas where we need to optimally configure and provision resources. So if we go to the different part of the management system for low latency, because we need to include new features, we need to define a new latency monitoring system. So this is the same system that Colin mentioned. And again, Docsis 3.1 low latency Docsis features and new Wi-Fi 6 quality of service scheduling are networking features that will enable us to support low latency services with more deterministic latency bounds. And we need a new marking system so that we can differentiate these low latency services to apply these features. And the service integration should be also supported so that customer requests may be taken into account. So how we can support such a new system? So there are three key points again that I want to emphasize. So low latency monitoring and management must be a part of end-to-end performance management system. Different networking improvements will enable us to abstract and program resources. And these resources may be cable modems, gateways at the home, or CMTS or routing functionalities in the headend, either in physical or virtual mode. And with software-defined network and network function virtualization, an orchestration system can use available measurements and data to program these resources. So to enable such a orchestration system, we can use machine learning techniques for a knowledge-defined networking. And open source products and standards will enable us service agility as a larger ecosystem can adapt this system. Then we can decide for low latency services if a cloud-based application or edge computing should be applied. And lastly, I want to say that security and accessibility should not be and later added on feature, but should be integrated starting from defining the requirements and designing the architecture. So that's the low latency management system that we are working on, and the recent improvements in the MSOs networks enable us to add low latency as part of the overall performance management system. So that ends my talk. Thank you, and I will give the access to Tushar Mathur from CommScope. Thank you.
Thank you very much, Sebnem. I see we've gotten some questions coming in on the Q&A on the portal. So keep those questions coming in and we'll get to them after Tushar's talk. So over to you, Tushar.
Thank you, Greg. So I'll try to complete this talk on latency by talking about low latency Docsis. So let me go to the agenda. I would briefly talk about why we need low latency Docsis, then what is the architecture and promise of low latency Docsis. And then we will dive deeper into the experiments that we did on the upstream portion of the low latency Docsis. It will have multiple parts. So first part will talk about a single service flow experiment. And we will have best effort scheduling as the scheduling type. for that experiment. And then in the second part of that experiment, it will also talk about PGS. And all these experiments will be done with incremental traffic rate to see the impact. Next experiment would be on single service flow versus low latency Docsis ASF. Classic service flow experiment. This is to make sure that the existing traffic is not getting impacted by low latency Docsis ASF. Third experiment will be the actual low latency Docsis experiments, where we will have the two service flows, one for low latency traffic and one for classic traffic. Then we'll recap and talk about some conclusions, and also the challenges and future improvements that can be done in this area. So I just want to briefly talk about speed versus latency today. So in the next generation networks, we not only require high bandwidth, right? Many applications also require latency. So in order to deliver the best quality of experience and quality of service, we have to keep in mind that latency is an important aspect. And gaming is one such application, like we heard in the talks before me from Colin and Shabnam. So, and gamers are also aware that latency is a big hit to them in terms of quality of experience. So low latency is also not just for gaming. I mean, it's for many different applications. It's just not limited to gaming. There are other low bitrate applications that can use it, such as VoIP or video conferencing applications. So it's an important topic. And low latency Docsis is supposed to help solve these problems. So now I'm going to talk about the architecture briefly, how low latency Docsis architecture looks like. So in low latency Docsis, there are two constituent service flows within an aggregate service flow. The first one is the classic service flow, and the other one is the low latency service flow. It can work, the ASF can work in both the directions, upstream and downstream. And in my talk, I will be focusing only on the upstream side though. So in classic service flow, we intend that all the queue building packets will flow through, and in the low latency service flow, all the non-queue building packets. Now, queue building traffic is mostly TCP oriented, and non-queue building traffic is mostly UDP oriented. So all the gaming traffic, which is generally UDP, should flow through the low latency service flow, and any kind of file upload or loading a video, that would be like queue building traffic. So that would flow through the classic service flow. There are added features from low latency Docsis. It has multiple tools. Some of them existed like AQM, but LLD adds a coupling to them. There's queue protection, and then there's classification of traffic to separate out the traffic. And on the CMTS side, there are functions like weighted round robin scheduler that would work between the classic and low latency service flow. It have the rate shaping for ASF like we have today for service flows. Then there's proactive grant service. That's another low latency Docsis add-on feature. And again, classification and AQM. So what are the goals of low latency? So we think that perhaps we can achieve 99 percentile latencies of under 10 milliseconds. And with more sophisticated optimizations like proactive grant services, it can be close to 1 millisecond. Now, low latency Docsis, it is going to be a software or a firmware upgrade on the CMTS and the CM in Docsis, and it will be Docsis 3.1 feature. Now, MSOs can use it immediately because it's a software or like a firmware upgrade, right? So it's a value added feature, and it promises to reduce latency in applications such as gaming, cloud gaming or multiplayer gaming, and also video conferencing or applications like VR or AR. So in the previous slide, I briefly talked about PGS, proactive grant services. So I wanted to give a description of what it is and what's the difference with the traditional Docsis request grant loop. So in a traditional Docsis request grant loop, when a packet arrives at the cable modem, it will send a bandwidth request to the CMTS, which will take delta 1 time. And then the CMTS will process that bandwidth request and transmit a bandwidth grant in the downstream that takes delta 2 time. And eventually the packet will be transmitted because it has the bandwidth grant. So the total time it takes in this whole process is delta 1 plus delta 2 plus delta 3. In the proactive grant services, the bandwidth grant is being sent by the CMTS without the CM asking for it. So it's like an active method of sending grants to the CM before the packets arrive, or as soon as the CM sees that the packets are starting to arrive. So it does not have to send a bandwidth request up to the CMTS, and it saves that time. So we call the portion where it receives the bandwidth grant and processes it as delta 2 dash. And once it has the grant, it can readily transmit the packet, and that is the delta 3 time. So PGS uses several parameters that are configurable on the CMTS or in the CM config file. These are guaranteed grant rate and guaranteed grant interval and guaranteed request interval. So in PGS, it would send the grants at a guaranteed grant rate and at a guaranteed grant interval. And this time, delta 2 dash plus delta 3 in PGS is much lesser than delta 1 plus delta 2 plus delta 3 time. Now PGS does not exclude the normal bandwidth requests to flow through. It will still allow any kind of normal bandwidth request to flow through along with PGS grants. So now I want to go into the experiments on the upstream that we have conducted using the real-world CMTS and real-world cable modems. Of course, the project is still under development, so the functionality and the numbers that we have can change over time. But this will definitely give an idea to people who are interested in this topic on how the LLD behavior is. So like I said, we focus on upstream LLD SF, and we generated 4 scenarios which had different traffic types. So scenario 1 had 2 gaming streams. One gaming stream in the case of LLD would always go into low latency service flow, and one will go into classic service flow and a web session. In scenario 2, I had similar things to scenario 1, but there were 2 OTT sessions and a speed test. In scenario 3, I had one gaming stream going into the low latency flow and the other one classic flow, and everything is same as scenario 2 plus a file upload. Scenario 4 is similar to scenario 3 plus 2 video conferencing sessions. So in these experiments, we configured the upstream AQM target latency to 25 millisecond. So in case of single upstream, single service flow, this was the target latency, and in LLD, the classic service flow target latency was AQM target latency was 25 milliseconds. We set the upstream target buffer to 50 milliseconds, and the upstream Tmax to 20 megabit and downstream Tmax to 100 megabit per second. So the reason we chose AQM target latency 25 milliseconds was because we want to try these experiments with a non-default value and see the behavior. The OFDM, the channels for OFDM and OFDMA, and we had developed our own methods to capture latency and jitter statistics for packets traversing through the different service flows. And all metrics in the LLD SF, like I said, had one gaming stream going into low latency and one stream going into classic service flow for measurement purpose. So this is the first experiment. This is our baseline experiment where we compared the best effort scheduling with PGS scheduling. And this used the base scenario 1, where I had 2 gaming streams and 1 web session going on. So in the single service flow, you can see with best effort scheduling, the mean latency was around 5.5 millisecond, and with PGS, it dropped down to 1.5 millisecond. Now, we did not have very highly optimized like PHY settings or max settings. We kind of took those values from MSO feedback. And you can see that the jitter values are also low with PGS, but the PGS efficiency, the usage of grants is kind of low because it's complicated and sophisticated on how you set up the different parameters for PGS. But with PGS, we observed that latency dropped by 72%. And I want to point out that all the jitter values are mean absolute packet delay variation values. Now this experiment, the second experiment, is with best effort scheduling, and it's all the traffic is in a single service flow. So S1, S2, S3, S4, these are all scenarios with incremental traffic. And on the left hand side, this graph shows 99 percentile and mean. So you can see that they increase as the traffic increases, right? All the queue building and non-queue building traffic is flowing through the single service flow. On the right hand side, I have 99 percentile and jitter values. And you can see the jitter rapidly rises, and the 99 percentile is similar to this graph. So mixing of the queue building and non-queue building traffic actually causes latency. This is what I want to do. This is the point that I want to make here. The next experiment is single service flow versus LLDSF classic service flow experiment. So in this experiment, I'm trying to compare that there's no degradation of queue building traffic if we go to LLDSF. So the solid lines are the classic service flow metrics, and the dotted lines are the single service flow metrics. So you can see it's all the 99 percentile and mean are actually pretty close to each other, and this is what we would expect. In this graph where I'm tracking the jitter, you can see a little bit of difference, but it still tracks pretty close. So the key point here is that the ASF, with ASF, there is no degradation of queue building traffic as compared to single service flow. Now we dive deep into the LLD experiment. So this is the actual experiment that demonstrates the division of traffic of queue building and non-queue building. So all the non-queue building traffic, that is the gaming traffic, it goes this first stream, it goes to the low latency service flow, and with best effort scheduling. So you can see that the mean value and the 99 percentile of the gaming traffic in low latency service flow is close to 5 milliseconds actually, and the 99 percentile was around 6 to 7 milliseconds. And the solid lines that show the classic latencies, you can see it rapidly rises as the traffic in the queue building flow increases. On the right hand side, you can see the jitter value for the classic and low latency. Jitter is so low for the low latency service flow traffic. So the key points that I want to make here is that separation of queue building and non-queue building traffic provides low latency to the non-queue building traffic, and even with best effort, you get pretty impressive latencies in the low latency service flow. And best effort can be used in low latency service flow. You don't have to necessarily use PGS. So this experiment is with PGS enabled in the low latency service flow. And you can see the latency is dropped so close to 1 millisecond, and the 99 percentile latencies are also close to 1 millisecond. And these are the dotted lines show the low latency service flow metrics, and the solid lines show the classic service flow metrics. So again, like classic service flow with queue building traffic, you can see the increase, and with low latency traffic, the dotted lines, you can see with PGS it dropped down even further. So one important observation to make here was that that it reduced the latency from 5 milliseconds to 1.5 millisecond, and jitter is very close to 0.1 millisecond. So some recap and then conclusions. So what we proved here was that the concept of separating the traffic in LLDSF helped us see better latencies for latency sensitive traffic. And an important point to note is that dual service flow did not see degradation of queue building traffic as compared to single service flow. So there was no degradation in the TCP behavior. We also observed extremely low jitter values when we enabled PGS. And either of the scheduling types can be used, best effort or PGS. We saw critical reduction with PGS, but it's complicated to use PGS. And we used real-world CMTS and LLD capable CMs to demonstrate this, and we generated bursty traffic that was developed using real-world statistics. Some of the challenges that we had, the CMTS and CM software were still under development, and even the spec was under development, so we had a lot of moving parts with different tool sets of LLD. And then standard tools are available by the spec in terms of histograms. But at the time when I was doing these experiments, these were not stable, so we did not have access to those. So we had to develop our own methods. And as Greg pointed out, the interop's still underway, and we are trying to solve all the problems that we can before they occur in the field. Also, it is important to note that tuning the PGS parameters for optimized use of upstream channel capacity and using the maximum sustain rate is it is challenging. And the last challenge is the adoption of traffic classification in the low latency and classic service flow at the application layer. So thank you for attending my talk. That's all I had, Greg.
All right, thank you very much, Tushar. So now we'll go on to some Q&A. We've got about 10 minutes for Q&A. Quite a few questions came in via the portal. And so let's kind of get to those. So first one, maybe I'll send this one to Colin. So what do you think, maybe it's a couple of questions actually, what do you think are the drivers to the really low, say sub 5 millisecond latencies besides keeping up with 5G marketing? And then how can LLD support holographic type communications with sub millisecond latency?
So I think the drivers, besides 5G and fiber to the home thing that they can do about a millisecond or so, are the customers. So the telcos are competing. They're saying we can do lower latencies than the MSOs, and so we got to match them in one way or another. Up here we have telcos that are heavily pushing fiber to the home, so we have that competing in a lot of our markets. We even have smaller ISPs doing fiber to the home from the get-go. Customers are starting to realize that latency is something that affects their quality of experience with gaming. So they'll look to this marketing to make their decisions on what ISP they go with.
Okay. Any thoughts about the sub-millisecond latency for holographic communication?
Yeah, so holographic communication, I don't think will require sub-millisecond any more than Zoom meetings or musicians playing together. The untrained ear, 100 milliseconds will be sufficient across the end-to-end network. Musicians, they start to fall apart playing together remotely around 30 milliseconds. So yes, keeping it lower is always better, but I don't think we need to get to like microseconds to allow holographic communications to continue. Holographic communications will be a lot on the bandwidth, so we got to make sure we can supply the bandwidth for those types of communications, and making sure that our latency doesn't suffer when we do push that much traffic through.
Okay, fair enough. Next question, I think probably for Shebnam. Did you run into any challenges with the RDK latency test measurement you mentioned for higher speed services like 1 gigabit per second? Is it hard to fill the buffers for the high rate speeds? And then kind of a follow-up to that, I'd add Comcast just announced a 1.25 gigabit per second symmetric service. And what new challenges do you think operators are going to face in terms of measuring speed, latency, and jitter across those ultra-high speed symmetrical service offerings?
Yes. So when our engineers worked on measuring 1.25 gigabits per second symmetrical speed tiers, especially in the upstream, it's a new speed and a significantly increased speed tier. So we had, I will say, we looked at it in two ways. One is our internal RDKB base or internal measurements where we can apply to other cable modems, but within our network by using the servers at the head end. So because, as you said, a lot of speed tests today is relying on the TCP-based traffic load. The trade-off between the TCP load and the measurement requirements is that we need to fill up the queues fast, but because at the client side, TCP connections may have different settings. Sometimes it's hard to fill up the queues and the speed TR in a short amount of time. So this is one problem that need to be investigated as, we are working on FTX and other future systems. And the other side is the customer side, because customers may use different third-party tools at home. And again, these tools may be based on a web browser algorithm. So it may also depend not only the TCP settings at the client, but on the web browsing settings, algorithms that they use, and also on the servers. So there are different areas that we need to look to make sure that we can support 1.25 gigabits per second and higher upstream downstream rate measurements.
Okay, very good. Next question, I think maybe for Tushar, but actually anyone can chime in on this one. How do we avoid the inefficiencies of wasted grants in PGS? How low do latency targets need to be to drive use of PGS versus just doing dual queue coupled AQM? And any idea what applications would need the super low latency created by PGS?
So I can answer the first part of the question for sure. So PGS is a bit complicated in terms of how you want to deploy it, because you have several tuning parameters associated with it, and you should have some sort of initially at least have some idea of like what kind of traffic operators to expect to put in the low latency service flows. There's definitely a need for some sort of adaptive methods to make sure that the grants are not being wasted, and that's something that we are actually actively working on.
Okay. Anyone else want to weigh in on that one? Okay, if not, I'll move on. Next question, I guess for Karthik. There's been a lot of buzz around cloud gaming recently. For example, Microsoft, Google, NVIDIA, Sony, Amazon, etc. They've all announced or launched these types of services. Will cable networks be able to provide both the bandwidth and ultra low latency that these services require?
Oh, that's a great question. I think traditional gaming, traditional online gaming is kind of, like I mentioned earlier, 60 packets per second, a few hundred kilobits per second upstream, maybe hundreds of kilobits downstream, maybe up to a meg. But some of these new cloud gaming services are definitely very downstream heavy, right? They're just encoding the video game as a video, or the game as a video, and sending it downstream. So that can get up to 25 to 30 megabits per second on the downstream. So I think on the bandwidth side, yes, definitely we can provide that bandwidth, right? Most cable services are above 100 megs and up to a gig, right? The question really becomes, can I give that lower latency as compared to other traffic within the network? And I think that's where some of the low latency Docsis technology comes in, and also the technology L4S, which the IETF is working through, and Greg is working on with the IETF, comes into play, right? The idea is there, you have a responsive congestion control algorithm, which can now vary the data rate as per the congestion on the network. And then the low latency Docsis technology gets and can classify this L4S type traffic into that low latency queue, kind of guaranteeing it that lower latency within the Docsis network. So I think with a combination of low latency Docsis and the L4S technology, the cable industry is getting well positioned to serve some of this cloud gaming markets.
Great, thank you. All right, we've got about 30 seconds left. Maybe one last question. I'll send this one Colin's way. This industry has been driven by the need for speed since the very first cable broadband rollouts, some 25 years ago. And based on what we heard in the opening session of this conference, there seems to still be some gas in that tank. Still interest in increasing speeds. But from what you've seen at Shaw, just kind of directionally, do you think there is a beyond speed in our future? And if so, how close are we to seeing other attributes like latency or other attributes becoming more important than speed for users?
I think we're getting to a point where we might have a bit of a pause in the need for speed, but definitely it's going to continue going forward. We're seeing multi-gig packages being offered up here in Canada. And latency during this pause will definitely become part of a customer's set of options to look for. They shop around for an ISP.
Okay. All right. Well, that's all the time we have for Q&A today. There were a few more I unfortunately didn't get time to ask, but let's all thank the panelists for those excellent presentations and responses to questions. Thank you very much.